Continuing through chapter 5, and we're going to talk about distributed loads. Then we're going to talk about doing that same process, the free body diagram, shear diagram, and moment diagram, using a problem with a distributed load. So the first thing I'm going to do is sort of talk about, we're going to go back and just sort of refresh a little bit on the sign convention. And what we have said is that we always have to do a cut section or a cutaway. And if we start at the left and cut on the right, a moment like this, a counterclockwise moment, is positive, and a shear, responsive shear down, is negative. If we go the other way, start on the right and cut on the left, that this type of a moment, which of course is still counterclockwise. Hold on a second, I want to make sure I got this right. Nope, got to do it the other way. This sort of a moment, which is clockwise, is positive, and this sort of a shear up is considered to be positive. So this is just a sign convention, and the reason that they oppose each other is because on that cut surface, you will have to have opposing moments and opposing shears in order to maintain static equilibrium. So the next thing that we're going to talk about today is a distributed load. And for the purposes of our discussion, I'm only going to talk about two types of distributed loads. One that looks like this, where you have a constant weight per foot, or load per foot, or load per length, referred to as W, small w. And then another one where we have a load that is triangular. In other words, it builds from one side to the other, where on one side, at one of the supports, that would be a fixed support, the load is actually equal to a small number or 0, and then it builds up to some maximum number, which we refer to as W0. But today I'm going to work a problem like this, and I'm going to borrow a problem, or I'm going to model it after problem 5.1, except I will use numbers, and then I assign to you for your homework this type of a problem using letters. Okay, so here, this is actually a drawing of 5.1 where we have a length of L, we have a fixed support and a rolling support, and then we have some sort of a distributed load. Now, last time I talked to you about the fact that when you have a distributed load, sometimes we model certain kinds of load, like traffic flow on a bridge, using this sort of an idea. And if we use numbers in this, let's just say, for example, that our length of the bridge is 7 meters, and the value of the load per foot is 20 kilonewtons per meter. Okay, so that's the value of W, and this is the value of L. Right? Well, the first thing that we need to do when we start to work with this is to realize that this type of a load is going to build reaction, and it's also going to build moment in a different way. So when we start talking about V, the first thing that we have to do is a free body diagram. So we need to determine what the overall load is. And here we have a load of 20 kilonewtons per meter acting over a length of 7 meters. So when we cancel out the meters, we see that the concentrated load equivalent would be 7 times 20, or 140 kilonewtons. Okay, so what that means for our free body diagram is that if we call this A and we call this B, that the reaction at A plus the reaction at B minus 140 kilonewtons has to be equal to 0. And that means then that R sub A plus R sub B will equal 140 kilonewtons. Now in this case, you can see that that load is symmetrical. So that means that the reaction at A, due to symmetry, is equal to the reaction at B. And so that means that each of them is equal to 140 divided by 2, or 70 kilonewtons. So when we draw this type of a distributed load, the first thing that we want to do is to state what our reactions are. 70 kilonewtons, 70 kilonewtons, okay? And then we have this W, which is 20 kilonewtons per meter for a length of 7 meters, okay? So this is a pretty good representation of our free body diagram. But what does our V diagram look like? Well, this is a little bit more complicated. It's not difficult, but we need to think about what's going to happen. In this case, let's say that I have this reaction at A, which is 70 kilonewtons. And as I go across the beam, and if I cut on one end, I also have this W force pushing it down. Now, if it was the entire length of the beam, the pushing down force would be 70 times the length, which is, or excuse me, 20 times the length, which is 7. However, here, it's just some arbitrary number from 0 to 7, which is x. Okay, so pushing down, I have 20 times x. That means that this is not a constant function, doesn't it? It means that it is increasing in magnitude as we go across the beam. So when I do my summation of forces in the y direction equal to 0, I get 70 pushing up minus 20x pushing down. Then this is pushing down in this case, so that's minus v equals 0. Or 70 minus 20x equals v. Well, what does that mean for my beam? What it means is that when I start here, I'm going to have x is 0, right? So that means that this is going to be 70. And when I get here, x is 70 minus 20 times 7, right? If I go like that, which is going to be 70 minus 140, or minus 70. So when I get here, the load is going to be negative 70. What happens between here and here? Well, we can do this in pieces if we want. We could say, what happens when x is equal to 2? At x equals 2, this number is going to be 70 minus 40, or 30. And when x is equal to 4, it's going to be, this will be 80, 70, that would be negative 10, right? The other thing you can see is that this equation is linear. In other words, this is an equation in x. V is a function of x, y equals mx plus b. And so it's going to be a straight line from here to here. And it's going to cross right here. Now, if you do the math, you'll see that this is directly in the middle of the beam. This is at 3.5 meters. But so this is what my shear looks like right here. So here's my free body diagram. Here's my shear diagram. And now here's my moment diagram. Well, the moment, of course, we have to draw a static, this is all statically determinate stuff, so we have to draw this and think about it once again, cutting, beginning at the left and cutting on the right. So here at A, we have a 70 kilonewton force, and then everywhere along the beam, we have a W is equal to 20 kilonewtons per meter. Okay, so what does that do for our moment? All right, now this is something that we're going to have to introduce a little bit of something here, but let's just look at this block. Here's my reactive moment, right? So what I can say, if this distance is x, we can first of all say that wherever we are, this moment is going to create a clockwise moment at a magnitude of 70 times x. So it's negative, right? Because it's going that way. Okay. Then this, all of this W, whatever it's doing, is going to create a moment going this way. So that's positive. So that's going to be 20 times x. That's how much force there is. But what's the distance? Well, the answer is this is a rectangle, and the distance is just like when we did, well, I don't know if I want to bring that in. When we looked at where the centroid was of a rectangle, when we were doing concrete, we found that it's right in the middle. So since this is a rectangle, the moment arm for that is x over 2. Now, if it were a triangle, it would be different. We're going to talk about that in just a little bit. But this is the moment from this force. This is the moment from this force. And then if I add to that m, because that is also counterclockwise, that has to equal 0. So what I get is a second order equation, or a quadratic equation. This term is 20 divided by 2, which is 10, x squared, minus 70x plus m equals 0. Or I could say m equals 70x minus 10x squared. All right, this is not a linear equation, is it? It's a second, it has a power of 2. So what is the shape of an equation that has x as a power of 2 in it? Yeah, it's either sloped or it's parabolic, isn't it? So that's exactly right. So here, first of all, if we look at this then, if we start thinking about what that moment equation is going to look like, what's it going to look like where x is equal to 0? Well, both of these terms have x in them, so it's going to be 0 right here, isn't it? What's it going to be right here? At 7, we're going to have 7 times 70, this is 490. 7 squared is 49 times 10 is 490. So it's going to be 0 again here. So that means it's going to be parabolic. It's either going to arch upward or it's going to arch downward. And that's the only thing that we really don't know. And since it's a parabola, the inversion point, or the vertex, is either going to be, it's going to be right in the middle, isn't it? It's actually going to be right in the middle where v is equal to 0. So let's find out what this looks like at 3.5 meters. I would get minus 70 times 3.5. No, I have to pull this over to the other side. Sorry. My moment is, let's see, at 3.5 meters. My moment then is 70 times 3.5 minus 10 times 3.5 quantity squared. And that's going to be the maximum value. If you remember, I'm not going to make you do calculus, but this actually, since this is 0, that's going to be an inversion point, or a point where the slope of the next curve down is equal to 0. So you're always going to get a maximum or a minimum moment at a point where the shear is equal to 0. But let's find out what that turns out to be. We have 3.5 squared multiplied by 10. So the value of the squared term is, this is negative 122.5. And 70, is that 70 or 7? 70 times 3.5. That value is a positive 245. So my moment is 245 minus 122.5 in the middle. And that is, oh, it's 122.5. It's exactly half. Okay, so it's a positive 122.5. So that means knowing that this is parabolic and knowing that it's 0 at both ends, I can see that right in the middle it's going to be 122.5, and that would be in units of kilonewton meters. So this is my moment diagram. Okay, now think about something else. We know from our previous work that a positive bending moment pushes it into a shape like this, right? A negative bending moment arches it upward. So if we look at the forces on this, does it correspond to this shape? In other words, will this load push this into a positive, does that look like a positive bending moment? If you push on it W all the way down, is it going to bend this way or is it going to bend this way? 1 or 2? 1. That is correct. So that is positive. So what I'm saying is that what we know so far corresponds with the fact that this is a positive bending moment. Okay? Now, another thing about this is kind of a way to remember this too. And I do not know, some people like this, some people do not. But if you can remember the shape of how a beam is bent, as to whether it has a positive bending moment or a negative bending moment, if you think about this as being like a little smile, smiles are positive, so get a positive bending moment if the beam is bent upward in a smiley face. All right, do you guys have any questions about this? All right, so what I want to do really briefly is to talk about what happens if we have a triangular one like this, because I'm going to assign you a problem like this as well. I'm not going to go through an entire problem, but I will show you how this works. The first thing, if we have a triangular thing like this, where this is W0 and this is 0, we still have reactions at A and reactions at B. Now the answer, first of all, is what is the magnitude of this concentrated load? Well, big W, if you look at this, what is this geometric shape right here? Is it a quadrilateral? No, what is it? 3 sides? Is it perhaps a triangle? Yes, it is a triangle. And what is the area of a triangle? 1/2 times the base times the height. Okay, so this is the applied load. So in other words, if W0 is 6 pounds and the length is 2 feet, the overall weight would be 1/2 times 2 times 6, which is 6 pounds. Okay? Now when we're doing this other thing, where is it applied? Well, it's always going to be applied, that W, whatever it is going to be applied at the centroid of the triangle. And the centroid of a triangle is not in the middle. In a rectangle, it's in the middle. In a triangle, it's 1/3 of the base. So the resultant force would be applied 1/3 of the way here. So when we look for R sub A and R sub B, we still know that's going to equal 6 pounds, but now it's not symmetrical. It's not 3 and 3. We're going to have to do moments about, say, point A in order to get that. And so we would get W times, this would be 2/3 of L. So this would be the weight, and this would be the moment arm, 2/3 times the 2 feet. And that pushes it counterclockwise, or clockwise, so it's negative. Plus R sub B times the entire length, which is 2 feet, equals 0. Then you can solve for R sub B, and from that you can solve for R sub A. Oops. There we go. All right, do you guys have any questions till you give this a go? Alrighty, so the 2 homework problems that I want you to get started with then are 5.1 and I want to take a look at, I don't really have another one that really is the same. See what you can do with 5.16. So far we have these 3 homework problems, 5.1, 5.2, and 5.16. 5.16 has numbers in it, instead of being a literal equation. So when we come back, we'll talk a little bit about literal equations, and that'll be Friday. We'll probably, and I'm going to show you a little bit more math as an assist in terms of a little bit of calculus-derived stuff to relate these three things to each other, but I will make it so that the problems you can use either way. If you prefer the graphical solution, you can do that. If you prefer a mathematical or arithmetic solution, you can, or you can do a combination of the two. All right, so that's it, gentlemen. We will see you Friday for more fun with mechanics and materials.